Okay, let's start class. So today we will talk about chapter 8. And I've already posted the slides in the Moodles. So we will only cover the first two sections. So section 1 and section 2 for the chapter 8. Okay, for the rest of the sections, I have the notes there. So if you are interested, you can read the notes. But for the final exams, it is comprehensive. It only covers up to the chapter 8, first two sections. I will talk about more about the final exams later. So chapter 8 is about to model the matched pairs. So the first question is, why we need to do the matched pairs? Because for the matched pairs, you can think it's complicated, right? Most of the statistic models, hypothesis test, inference like a confidence interval. So we have a very, I would say, like a universal assumption is the independence assumption. But for the matched pairs, it's not independent anymore, it's dependent. Okay? And why? We need to do the matched pairs. And there are strong reasons that why we need to do the matched pairs. Okay, so first let's see what is the matched pairs. So when we compare the categorical response for two samples that have a natural pairing between the two samples, then the response in these two samples can come from the matched pairs, and that is called statistically dependent observations. Okay, so by doing the matched pairs, the most benefit from the matched pairs is very similar to the randomized block design. So when you design an experiment, why we need to use the block design? Because when we use a block and observations in the block can be assigned to different treatment. But the good thing for the observation within a block, although they apply to different treatment, they are more homogeneous, right? Homogeneous means what? Means that they controlled for many other confounders. Like, for example, if we have a few types for the rice, we want to see the fertilizer's effect on the yield of rice. So we can have a block. We can have this plot split into four part subplot, and we can apply to four different fertilizers. And another plot split into four part, apply to four different fertilizers. And we can check their yield to see the fertilizer effect. Why we need to do that? Each plot is a block, because if we have these four treatment applied to the same plot, that means we control the moisture levels, the irrigation methods, the temperatures, because these confounder factors, confounding factors are almost the same within the same block, within the same plot. Just like that, for the matched pairs, if we have a matched pairs, and these matched pairs apply to different treatment, then the variations will be controlled. Okay, so that's the purpose. So that's why in many studies, we have a matched paired study. For like in the clinical trials, if you have two types of skin treatment, okay, and you can apply to two arms of the same patient. One arm randomly picked and applied the treatment A, another arm applied to the treatment B. on the same patient. So we can see their effects on both arms. Why we need to do that? Because different people, they have different schemes, they have different activities, they may affect the results, right? But if you apply to the same treatment, same person, two different treatment, you can easily see and compare the results, because all the other factors like the genetics, activities, diets, any other confounding factor will be controlled on the same person. Okay, so that's the main reason why we need to use the matched pairs. So here, this is the outline for the chapter 8. But as I said, we will only focus on the first two sections. Okay, so the first section is comparing the dependent proportions for the binary matched pairs. And section 2 is the marginal models and subject-specific models for the matched pairs. Okay, and the rest of the sections I will not cover in this course, and also in the finals will not cover, is extended from the binary to the multi-category nominal response, and also extended to the ordinal response, and then to the rater agreements and the Bradley-Terry models. Okay, but these are not covered. But I have the notes there, so if you are interested, you can read the notes and the textbooks. So for the chapter section 8.1, we are comparing the dependent proportion for the binary matched pairs. Let's see an example first. So this data is from a general social survey. So the subjects were asked whether to help the environment, they will be willing to have two questions. First is pay higher tax or accept a cut in living standard. So they will ask two questions. First is, in order to help the environment, are you willing to pay higher tax or not? You need to answer yes or no. Okay. And the second question is, in order to help the environment, are you willing to cut the living standard? Yes or no. So each person asked two questions. Okay. So in this study, you can see we have two variables. One is the paying higher tax, yes or no. And one is cutting living standard, yes or no. So both questions are binary response. Is that right? And also each person is matched with himself, because each subject is need to answer two questions, both questions, right? So that's why for the same person answer two questions, these two responses are correlated. They are not independent. So this study is very different from you ask one group of subject question 1 and ask another group of subject question 2. They are very different, because in that case they are independent answers. But here they are dependent. They are matched within the same subject. Okay, so the response from the same person is correlated. Okay, so we can see the here the odds ratio is 10.9. So 10.9 means what? 10.9, that's the odds ratio, means the odds of answering yes for one of the question, let's say for question 1, will answer also yes for the question 2 is almost 11 times as high as for the subject that answers no for the question 1, right? So odds ratio is 10.9. That means there's a high agreement for answering the yes for the same subjects. Okay, so that shows they are highly correlated. They are not independent. So the answers for the question 1 and answers for the question 2 are strongly associated by the odds ratio, right? So now here, let's say, suppose we want to test the proportions of the subject that will answer yes for the question 1 is the same as the proportion of the subject will answer yes for the question 2. Okay, so here in this table, we can, so the null hypothesis is pi 1 plus minus pi plus 1 equals to 0. Is that right? So we can write in the mathematical ways, so as that. So pi 1 plus, that's the marginal proportion of answering yes for the first row, right? And pi plus 1 is the marginal proportion of answering yes for the first column, right? So we want to see if these two are statistically is the same or not through the statistical test. Okay, and we will see the difference is statistically significant or not. But for this one, we cannot treat it as independent observations because they are dependent. They are correlated, they are matched within the same subjects, right? So we need to do a test that can count for the dependence. So here, let's take a look. So what is the pi 1 plus? So pi 1 plus is equals to what? Equals to pi 1, 1. So that's the proportion for answering yes for both question 1 and 2. Plus pi 1, 2. Is that right? Pi 1, 2 is answering yes for the first question, but no for the second. By adding these together, that's the proportion of the subject answering yes for the first question, right? And what is pi plus 1? Pi plus 1 is pi 1, 1 plus pi 2, 1. So both pi 1, 1 and pi 2, 1, they answered yes for the second question, but pi 1, 1 also answered yes for the first, but pi 2, 1 is for the first question answers no, but second yes, right? So in order to do that, if we decompose it, so this becomes to pi 1, 1 plus pi 1, 2. Is that right? Then this one becomes minus parentheses pi 1, 1 plus pi 2, 1. Is that right? We want to test they are equals to 0 or not. Then you can easily see pi 1, 1 and the pi 1, 1 canceled out. So that is, this test is equivalent to what? Is equivalent to pi 1, 2 minus pi 2, 1 equals to 0 or not. Is that right? So this test is equivalent to testing this proportion, which is switching from yes to no, right? The proportion of subject that's switching from yes to no for the first to the second question is the same as the proportion of switching from no to yes for the first to the second question. So these two proportions are the same or not. If they are the same, then the marginal proportion of yes is the same. If these two are different, then it will be different, right? So this is mathematically equivalent to this one. Okay, so And what we can do is, this is a standard McNema test for testing the marginal homogeneities. Okay, so the null hypothesis is pi 1 plus minus pi plus 1 equals to 0, which is equivalent to this. Okay, then under the null hypothesis says they are the same, right? So these two are the same. So then we can just use N12 and M21. That's the frequency. That's the frequency for the switching from yes to no and no to yes in these two cells, off-diagonal cells, follows a binomial with N star and a half. Remember the binomial? Binomial distribution had two parameters. The first one is the number of trials. What is N star? N star is N12 plus N21. That's the off-diagonal total. Okay, and 1/2, that's the proportion of answer yes. I mean, the proportion of being success in that binomial trial. Right? Okay, so this can be viewed as a binomial with the total number of trials is the off-diagonal totals, and the proportion that falls into one of the off-diagonal is 1/2, and the other off-diagonal cells is also 1/2, right? So we can do it through the binomial. So McNema test is nothing but a binomial test to test with the p equals to 1/2. Okay, so if we have large enough sample size, and you may ask why is m star is greater than 10? Because remember, for the binomials, we need the MP is what? For the binomial test, usually we need the MP is greater than what? Greater than 5, right? And the m times 1 minus p is greater than 5. Remember that? These are the conditions that we need to have for the binomial test. But here, what is the p? Under the null hypothesis, p is what? 1/2. So here the p is 1/2. And 1 minus p is also 1/2. So in order to get to n times 1/2 is greater than 5, so you can see why we need to have the off-diagonal total is greater than 10. So that's where this 10 comes from. Okay, and you may ask why we need NP greater than 5. So that is based on the central limit theorem. Okay, so central limit theorem says that if we have large enough sample size, then the sampling mean will follow approximately a normal distribution. Okay, so if we have large enough off-diagonal totals and under the null hypothesis, then we can use the McNema test study, which is this one. And this is equivalent to this. And that follows a chi-square distribution. Okay, so these from here to here, that's just simple math. There's nothing tricky. Just to replace the n star by the m1, 2 plus m21. Okay, replace that and then multiply 4 on both numerator and denominator, and you can easily get this. Okay, this is just a very simple math. You can do it after class. And this follows a chi-square distribution with degree of freedom is 1, given under the null hypothesis. Okay, so if we have a very large test studies, so that will lead to rejecting the null hypothesis. Okay, if the test study is small, then we will say, okay, so we fail to reject the null hypothesis. So in this study, the environmental opinion study, so the z square, the test statistic is 132. That's the N12 minus N21. That's 107. So see that that's n12 minus n21. Okay, so 132, 107. See that? Take the square, then divide by the off diagonal total. That's 132 plus 107. And that equals to 2.62. And that follows a chi-square with degree of freedom is 1. If you go to the chi-square table, you will see the p-value is around 0.1. So 0.1, that means we have very weak evidence, not very strong. Usually we use 0.05, right? So this is 0.1. So it's kind of marginally significant, but on the weak side. Okay, so we see there is a small difference. Okay, in terms of the marginal homogeneity. But if we use 0.05 as a cutoff, it's not significant. Okay, so in the R, if you want to do the McNemar test, there is a function in the base package. You don't need to download any libraries. So that's called McNemar.test. Okay, and here there's an option called correct. So that means the continuity correction. Okay, so this we usually don't use that because that will usually lead to too conservative results. So we just said the correct is false, and that gives you the p-value, which is the same as this. Okay. So that's the McNemar test for testing the marginal homogeneity. And sometimes when not just focus on the hypothesis test, we also would like to use the confidence interval because the confidence interval is more informative than a significance test. And that is actually very important, okay, message. So in practice, when you do the statistical inference, if you only do one approach, I would rather prefer the confidence interval instead of the hypothesis test, because the confidence interval give us the hypothesis test results, right? There is an equivalence between the confidence interval and hypothesis test. So we can do the hypothesis testing through the confidence interval approach. Remember that? So if the confidence interval includes the hypothesized difference, then we say there's no significant difference. If it does not include, then we say there is. Of course, the significance level and the confidence coefficient should be matched. Okay, like if you are doing the significance level for 0.05 for the hypothesis test, you should use the 95% confidence interval, right? And so you can see the confidence interval gives you all the information that you can get from the hypothesis test. But also confidence interval can give you more because sometimes, as I said several times before, the researcher is more interested in the practical significance than the statistical significance, right? So if we have a confidence interval, that also can tell us if there is a practical significance or not. Usually, let's say we have 2 treatments, okay? And we use the confidence interval to test the difference between these 2 treatments through a numeric measure, okay? And I have a confidence interval. And suppose in practice, we have to have at least that difference, a certain difference, okay? Let's say at least we have to have the difference delta to be no less than 0.1. That can be lead to a practical significance, let's say, okay? Then if we look at the confidence interval, If the confidence interval does not include that, that means the confidence interval shows that there is a practical significance between the two treatments. Let's say if the difference between two treatments has the confidence interval is 0.2 to 1.9. Okay, so you can see the lower bound for the confidence interval of the difference between the two treatments is bigger than the delta, 0.1. And that is usually, let's say, in this field, we usually commonly say if the difference is greater than 0.1, we say there is a practical significance. And that confidence interval tell us, okay, these two treatments does have a practical difference. You see that? We can do that. So through that confidence interval, we can not just telling the statistical significance, but also can tell us more information. Okay, so that's why in practice, if I choose just one, either hypothesis test or confidence interval, I will usually use the confidence interval. And also, if I review a paper, I prefer to look at the confidence interval instead of just the p-value. Because p-value, I can only tell statistical significance, but nothing more than that. Okay? So for the confidence interval, for the difference between the two dependent proportions, this is the standard error. Okay? And the 95% word confidence interval, that testing that shows the marginal difference, okay, is our observed marginal difference plus minus 1.96. Why is 1.96? That's the 95% critical value from the standard normal times the standard error. Okay, so that's the 95% word confidence. So usually we can use word confidence interval. However, if we have a small total of diagonals counts, so if we have a small m star, or if the the marginal proportions are either near 0 or near 1, then the word confidence interval will usually have a very wide confidence interval. Okay, so that can well below the nominal levels. So in that case, what we can do is we can have a simple fix is to add 0.5 to every cell before applying the word formula. Because when the marginal proportion are very close to 0 or 1, that means what? That means some of the cells we have 2x2 tables, right? Some of the cells it's very likely to have very low count, very low value counts, or close to 0 counts. So we just add 0.5 to all 4 cells. 0.5, add 0.5 to all the 4 cells. Okay, and then we apply the 95% word confidence interval. So that will lead to more accurate, okay, results. And another option is instead of using the word confidence interval, we can use score test based confidence interval. So both approach are easily available in R through this package called the prop confidence intervals, prop CIs. Okay, so if you want to find out these two confidence intervals, just use the download and install the library prop CIs, and then use the function diff propci.word.mp, and this is the score ci.mp. So these two functions gives you the word confidence interval and a score test-based confidence interval. Okay, so from this study, we have the 95% word confidence interval is this one. So you can see the 95% word confidence interval does include 0, but the lower bound is very close to 0. So this also tells it's kind of like marginally significant because the lower bound is very close to 0, right? And these agree with the test results. Okay. So the McNeema test and also the confidence intervals, you can see these are not a function of the diagonal elements, but a function of the sample difference. You can see like the McNeema test is only involves the M12, M21. These are the off diagonals, right? These are only the off diagonals, only those off diagonals. So the diagonals are these N11 and N22. They are not involved in the McNeema test. And neither for the confidence intervals. If you look at the confidence intervals, only involves N12 and 21s. Okay, why that is the case? Because the test or the confidence interval is really about what? Is really about the difference for the marginal proportions. So the test, the McNeema test and the confidence interval is really about testing the pi 1 plus and pi plus 1's difference or not. So for these are really about what? Are really about the switching proportion. Is that right? So the test is really about the switch from yes to no, and for the first to the second, or from yes or no to yes, from the first to the second. So it's really about the switching proportions. So it's not about the diagonal. What are the diagonals? The diagonals proportions are the agreements. So this is not about agreements, but about the switching proportions are the same one. So that's why for the McNeema test and for the confidence intervals, it only relates to the M12 and M21. Okay, so if you are familiar with those sufficient statistics, if you are taking the our statistics theory courses, you should know that the M12, M21, these are the sufficient statistics for the McNeema test and for the confidence intervals. Okay, so here in this environment survey study, so you can see the switching proportions is 37% who are willing to pay higher tax are not willing to cut their life standard. So you can see the switching proportion is 37% from yes in the first question to the no for the second. But for the no for the first and switch to the yes is 32%. Okay, so that's why it's marginally significant because the difference between these is only 4%. Oh, no, 5%, I'm sorry. And that 5% is not that big enough. So it's kind of marginally significant at 0.1 level. Okay. Okay, now a straightforward extension for the McNeema test is instead of having the binary response, we can extend it to more than 2 categories, right? So the generalization of McNeema test to the square tables with C by C. C is no less than 3 is often referred to as the generalized McNeema test, also called the Stewart-Maxwell test. Okay, so the null hypothesis is just like the McNeema test. It says that the marginal proportions are the same for all the row and columns. So in other words, that's like here. Let's see for this example. So this example is we have 88 patients. Okay, before they entering diet therapy study, they first asked questions about their cravings for the certain high-fat food products. Okay, and they have 3 options: either never take these high-fat food products, or occasionally or frequently take this food. And after these 2 weeks diet therapy program, and they will ask the same question again. So it's a pre-post study. Okay, so after 2 weeks, they will answer the same questions, and these are the results. So just like McNeema, this is a matched within themselves, right? So, but instead of 2 categories, we have 3 categories. Okay, so what is the null hypothesis for the Stewart-Maxwell test? The null hypothesis is the proportion of answering the never is the same in the pre-study as the proportion after 2 weeks. And the proportion of answering occasional in the pre-study and after 2 weeks are the same. And the proportions for the frequentist, for answering the frequent, for the pre-study and the post-study are the same. Okay, so you can see the null hypothesis actually involves 3 equations. Pi 1 plus equals to pi plus 1, and pi 2 plus equals to pi plus 2, and pi 3 plus equals to pi plus 3. Okay, so that's the null hypothesis. And the alternatives is at least one of them are different. One of the equation does not hold, at least. Okay, so this is the generalized McNeema test. Okay, and there is an alternative test also can do the same test. That's called the Barker's test. So for the Barker's test is asymptotically equivalent to the Stewart-Maxwell test. Okay, so what is asymptotically equivalent means? Asymptotically equivalent means that if the sample size increases to infinite, larger and larger, larger and larger to the infinite values, and the test results from the Barker's test and from the Stewart-Maxwell test are exactly the same. So that's called asymptotically equivalent. Okay, but of course, this is just a statistical property. In practice, we will not have very large samples. So for the finite sample size, empirical studies shows that the Barker's test is generally considered to be more powerful than the Stewart-Maxwell test. In other words, for a not too large sample size study, if you can use the Barker's test. instead of the Stewart-Maxwell test, okay? Because the Barkhouse test gives us usually high powers. Okay, so here in this study, I highlighted two cells. Okay, one of the cell is this one. One is this one. So I just show you that for these two cells, it shows some signs of the significant switching. Okay, for the 12, that means for the pre-study, we have 12 subjects answers frequently would like to have this high-fat food product, but switch to the occasional after 2 weeks program, diet therapy program. So you can see that 12. And also we have 9 subjects switching from occasional to the never after 2 weeks program. Okay, but I use different colors. Why? Because you can see that although these two numbers are both quite large comparing to the sample size, 88, but this one is more significant, has more influence on the test results. Why? Because think about, this is about the symmetric off-diagonal elements. Do you know the symmetric? Like if we want to compare N1, 2, we have to look at N2, 1. Is that right? If we look at N2, 3, then we should compare that with what? N3, 2. Right? It's symmetric. You see that? So if we look, if we have 12 here, what is the baseline you want to compare? You want to compare with this one. This is the switching proportion, switching number for switching from occasional to the frequent after 2 weeks program. So you can see 12 is, you should compare with 2. But what about 9? 9 is from occasional to never. So when you do the comparison, you will need to compare with from occasional, from never to occasional, right? So you should compare with these. So 9 compare with 6 and 12 compare with 2. And you can see which one is more significant. Of course, it's 12. So I'm just telling you, for these matched pair studies, okay, we should focus on those switching proportions or the frequency for these off-diagonal cells. But you also need to do the comparison, right? How large is large? You need to also compare with its symmetric, that switching spot, okay? Like here, the 12, you need to compare with 2. Then you can easily see, wow, there is a significant, probably there's a significant difference that's switching from frequent to the occasional, right? But for the occasional to never, it doesn't seem to be that significant because 9 and 6, they are quite close. Okay, so that's how you read the tables. Okay, now let's see. So this is the data matrix, and for the generalized McNeema or the Stewart-Maxwell test, this is the function called the Stewart-Maxwell test. You can use that test to do this Stewart-Maxwell test, or the also called the generalized McNeema test. And you can see the degree of freedom is 2. Why is 2? Because the null hypothesis actually involves 3 equations. Remember, pi 1 plus equals to pi plus 1, and pi 2 plus equals to pi plus 2, and pi 3 plus equals to pi plus 3. But we have these three equations, but only two of them are redundant. Two of them are non-redundant. The third one is redundant. Why? Because the third one is what? We can write as 1 minus pi 1 plus minus pi 2 plus. Is that right? Equals to 1 minus pi plus 1 minus pi plus 2. So you can see the third one is redundant. So the only degree of freedom is what? Is 2. So that's why the degree of freedom is 2. Is that clear? So that's the so you can see the p-value is 0.049. So that tells us there is a marginally significant difference. Okay, for at least one of the equation does not hold. Okay, and now if we do the Barkhart test, you can see here the p-value is 0.038. So which one has more significant results? Of course, you can see it's the Barkhart test. So that's why this one has more power. Is more powerful, right? Than the generalized McNeema test. Okay, and after that, so you can see these two tests only give you the overall results. It tells you there is a significant difference for at least one of the equations. But which equation is different? It doesn't tell you, right? So in order to find out which either the pi 1 plus, which equation is different, then you have to do the McNeema test in a pairwise way. So here I do the McNeema test for comparing the first two rows, McNeema test for the last two rows, and the McNeema test for the first and third rows. Okay, and for all these three pairwise comparisons through the McNeema test, you can see there is a significant difference for testing the second and third rows. Second and third rows. Okay, so what is the second and third rows? Second and third rows is what? Is occasional to frequent. You see that? That's why I highlighted 12 in red. So you can see that gives us significant difference because comparing the 12, we only have 2 that switch from the occasional to frequent. But we have 12 switching from frequent to the occasional. So that leads to a significant difference. Okay, so that is the generalized McNeema test to more than 2 categories. Okay, any questions so far? Okay, so the section 8.2, that's the second section, okay, is doing the same thing, but through a different approach. Instead of doing like the simple test, like McNeema test or generalized McNeema test, we do the same inference, but through the modeling approach. Okay, so here we can do the 2 types of modeling approach. Okay, one is called the marginal models. Okay, and the second is called the subjective specific models or the random effects models. Okay, so section 8.2.1 is talking about marginal models. And the next section is talking about the subject models. So these are the 2 modeling approach for the matched pairs. Okay, so let's first look at the marginal models. So for the marginal modeling approach, okay, we can use identity link or use the logit link. That's so just like using the doing the probit regression or the logistic regression, okay, with the different link functions. If you use the identity link, we can model the probability of answering yes. Okay, here we have an index for T. T is the index for the question 1 or 2. Okay, so question 1, what is question 1? Remember, question 1 is to increase the tax rate. And question 2 is to cut the living standard, right? So equals to 1, that means answering yes for the question 1 or 2 can be modeled by the alpha plus delta xt. So what is xt? xt is the index for the question 1 or 2. If it's question 1, then we have the xt equals to 1. If it's question 2, we have the xt is 0. Okay, so what is delta? Then the delta is the difference between the marginal probabilities. And in this case, what is the baseline group? Baseline group is the question 2. Because the question 2 is what? Is having the x2 equals to 0. Okay? So an alternative model, we can do the logit link. So instead of modeling the probability, we model the logit equals to alpha plus beta xt. Okay? So here you can see what is the alpha. Alpha is really about the agreement. So for the diagonal elements, n11, n22, these are the contributor for the alpha. But how much they agree to each other. But what is the delta and the beta here? Delta and beta, these are about the difference between the two questions in terms of the probability or in terms of the logit, right? So the beta and the delta, these are really from the N12 and N21. These are the off diagonals. You see that? Okay, we will see more in the next slides. So delta is the difference between the marginal probabilities, and delta is the difference between the marginal probabilities, and the beta is the log odds ratio that comparing the marginal distributions. Okay, so these methods are called marginal models. Why? Why is it called marginal models? Because these only focus on what? Yt equals to 1, that's the marginal probability. So they only focus on the marginal distributions to response. Okay, so for the marginal models, the most common approach, the most common tools that we use to do the marginal model is called the generalized estimating equations. So we use the GEE to fit the marginal models. Okay, and the estimate for the delta is this one, and the estimate for the exponential beta hat is this one. So you can see the delta and the beta, they are both involved in what? N1, 2 and N2, 1. Remember? So these are really about this. Like here, this minus that is nothing but N12 minus M21. Oh, N21. Okay? So these are really about the difference. So the hypothesis for the equal marginal probability for the McNeema test is just testing the delta equals to 0 for the identity link, or beta equals to 0 for the logit link. So that gives you a connection between the modeling approach and the testing approach that we talk about in the section 8.1, okay? So we can, instead of doing the McNemar test, we can also use these marginal models to do the test. Okay, so here, this is still the same data set, the environmental opinion study. So I use the library GEE. That's the library, our library to do the generalized equation estimating. Okay, so you can see the main function is GEE. I use the fit equals to GEE. Y is the response, and the question, we have 2 questions for each person. So the ID is person, okay? So here, the data format for doing the GEE is in this way. So for the person 1, it has 2 rows. The first row is the person 1 for the question 1, and that's that person is for the answering yes. For the person 1 and the question 2, that person is answering no. So like that. This is the format. Okay, so for this, we have the oh, I'm sorry. For the question 2, it also answers yes. We have the Y is yes. So after fitting this, and here I use the family is binomial, but the link is identity link. So this is the first approach using the identity link. And you can see here, this is the results. In the results, it has 2 standard errors and test statistic Z. One is the naive standard error and the naive Z. One is the robust standard error and robust Z. Okay, so what's the difference? The naive, so the estimate is the same. Okay, but the standard error, it has 2 standard errors. Naive standard error means that here it assumes the person's answering the first 2 rows like the person wants, these are the independent. Okay, but robust is they're dependent, they are from the same person. So the naive assumes this study, so we have 88 persons answers for the question 1, and a different group of 88 persons answers the question 2. So naive ignores the pairing structure, okay? And robust standard error and robust Z, these considers the matched pairs. So that means we only have 88 persons, but each person answers 2 questions. Okay, so in this study, of course, we should use the robust. So robust standard error and Z, these are more appropriate for this case. And the fit 2 is using a different link. That's the loaded link. Okay, so you can see here, the results are different and you should interpret in different ways. Okay, so for the identity link, you can see here the delta is 0.022, right? So that's for the question. So that means what? So that means the estimated difference of the proportions for answering yes in question 1 and 2 is about 2.2%. Okay, and the model with the loaded link, the beta is this one, 0.1035. Okay, and if we take the exponential, so that will be the 1.11. Okay, so how do we interpret? We should interpret the population odds of willing to pay the higher tax are estimated to be 11% higher than the population odds of willing to accept the cuts in the living standard. So that's how we interpret differently if we use different link functions. Okay, so that's the marginal approach through the generalized estimating equations. Okay, so the section 8.2 is about a different modeling. 8.23 is about a different modeling approach. That's the subject specific approach. Okay, so here the binary matched pair data can alternatively present the data in n separated 2x2 tables. Is that right? So for each subject, we have a 2x2 tables. Okay, so for this subject, for the, let's say for the subject 1, we have this table showing the question 1, paying higher tax is yes or no. And for the question 2, for this same subject, for the cut the living standard, yes or no. So that's the table for this subject, for the first subject. And we have this table for all the subjects. Okay, so then we can have the population average tables. So if we average all these tables together, then we will have these entire tables. So that's called the population averaged tables. So among all these subjects, we have 227 subjects answers yes for both, and 678 for both no. And this 107 is no for the first question, but yes for the second. And for 132 is yes for the first, no for the second. Okay, so then we can do it through the randomized, through the mixed effect models. Okay, so that is for each subject we have a model. So like here we use the loaded link, and we have the T is the index for the question 1 and 2, and I is the index for the subject. So we have 1,144 subjects, right? So that's the I's subjects. For that's the logit equals to the alpha I plus beta xit. So here the alpha I is the random effects. Why? Because this changes among the individuals. And that allows the subject to subject variations through this intercept. And the beta is called a fixed effects. What is fixed effect? Fixed effect means that the difference of the proportions is the same among all the individuals. So beta is the fixed effect, and the alpha is the random effect. So this model is called a mixed effect model. Okay, so here we can have the probability of answering yes. For the question 1 is this one, for answering no is this one. But here, how many parameters do we need? We need m plus 1 parameter. Why m plus 1? Because we have n alphas, one for each subject. Y plus 1, 1 is from the beta. We have 1 parameter for the beta. right? So we have n plus 1 parameter, but we only have n data points, n subjects. So you can see we cannot really estimate all the parameters appropriately. So a simple way is what? Is instead of estimating all these parameters, we only estimate beta. Does it sound familiar to us? Yes. This is what? This is exactly called conditional logistic regression that we talk about. Remember, we talk about conditional logistic regressions, right? So instead of estimating all parameters, we're only estimating beta. Why we don't estimate alpha? Because these are random effects. We don't really care. We do not really care about that. That changes for each individual. But we really care about the beta to see if there's a difference of the proportions for these two questions, right? So we can use the conditional logistic regression for the matched pairs. Okay, and the inference for this model focus on the betas. And we use the CLR, conditional logistic regressions, that maximize the conditional likelihood without estimating the alpha. Okay, and for the conditional maximum likelihood, we can see the beta hat is really the log of n12 divided by n21. You see that that's still only based on what? Only based on the off-diagonal counts. Okay, and the standard error is this one. You can see the estimate, the conditional maximum likelihood estimate and the standard error is very simple. And the proof actually is not difficult. So if you are interested in the proof, why this is this one, you can look at the categorical data analysis, third edition in section 11.2.3. This is a different book from our textbook. Our textbook is the introduction to categorical data analysis. But this is the categorical data analysis, but by the same author. So they are both from Agresti, okay? But our textbook is a simplified version without those proofs. But if you, the categorical data analysis, this is a more technical textbook, which we didn't use, but just as a reference. So if you want to see the proof, it's in the chapter 11, section 11.2.3. It shows you the proof of that. So for the environmental opinion example, we have the exponential of beta hat equals to 1.23. So that means assuming the model holds, a subject's estimated odds of a yes response are 23% higher for raising the tax, that's question 1, than accepting a lower standard of living, that's question 2. That's how we interpret. Okay, and the odds ratio is 1.11. So that is found in the marginal models. So you can see there is a difference using the GEE for the marginal models and using the subject specific models. Okay, so here, which one is better? Personally, I prefer this one. For the GEE, that's a simplified version. Okay, it's quick and easy way, but using this conditional logistic regression is more appropriate. Okay, so I interpret the conditional logistic regression through the mixed effect model, but mixed effect model is kind of different. It's really different from the logistic or conditional logistic regression. It's not maximizing the conditional likelihood. It's actually maximizing a different type of likelihood function. But this is a mixed effect model, but we can solve it through the conditional to maximize the conditional likelihood. That's called the conditional logistic regression. Okay, if we use a different type of likelihood to maximize that, that leads to the results for the mixed effect model. Okay, so this is the another example. So this is the low birth weight study, that's the matched case control study. So in this study, we want to study the effects on birth weight matched each case in which the child were underweight with a control in which the child had normal weight. And then we checked their mothers who were matched according to their age, were asked whether they were smoker or not. So we want to see the smoking effects on the birth weight through a matched case control study. Okay, so here this is the results. So the conditional maximum likelihood for the odds ratio is 2.75. Okay, which is the ratio for the off diagnose, 22 and 8. That's 2.75. That's the conditional maximum likelihood. Okay, and the odds ratio is 2.75. So that means the odds of having the normal birth weight among the non-smoker is 175% higher than the odds among the smokers. So all these tests are significant, and this is the results. These are the code in the R's. Okay, so from from section 8.31, we will not cover that. So that is extended from binary to the multi-categories and using different models. It's like the baseline category logic model. Okay, so let's stop here. Any questions for chapter 8, first two sections? Okay, so before we stop, I've already posted the slides for the chapter 8. Okay, and also I have the exercises problems also posted, and I also have the announcements for the final exams. So the final exams is scheduled on May 5th. That's by the universities. So that's Monday, 12:30 to 2:30. So we have 2 hours. Final exam will be comprehensive, but not including the Bayesian part. So for the Bayesian part, it will not be included in the finals. It only covers from chapter 1 to chapter 8, section 8.2. Okay, so from chapter 1 to chapter 7, these are 4, and the chapter 8 only for the first 2 sections. Okay, like exam 1 and 2, you can bring 3 piece of papers. 1 from the exam 1, 1 from the exam 2, right? And then you can have an extra ones. That's for the final exams. And you bring the calculators just like before, and it's closed book, no closed notes and closed computers. So the place for the exam will be the same as exam 1 and 2. That's room 44, Wuding Hall. So I will provide the tables just like before. So you don't need to bring the tables. Okay, so I will not give you the old exam for the finals, but the format will be the same as exam 1 and 2 because you've already have the exam 1 and 2. So you know what type of questions you will see in the finals. So basically, the only new material will be added is the chapter 7 and the chapter 8 first 2 sections. The first 6 chapters are already covered in this exam 1 and 2. So that's the only new part will be added into the finals. Any questions? And don't forget, we will start to do the presentations on Wednesday, and the attendance is required. And I've already have 4 students volunteered for the for presenting on Wednesday, this Wednesday. Okay, so I have 2 for the next Monday, and I will send out the emails for who will present and what is the order for Wednesday, for this Wednesday, and for next Monday. And if you would like to volunteer to present on Monday, next Monday, just let me know. We have 2 spots available for next Monday. And the rest 3 will present on next Wednesday. Okay? Any questions? Okay, if you don't have any questions, let's stop here.